Hello everyone, welcome to our channel. This is Dinesh MA, working as Assistant Professor in the Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. Today's session we will understand the concepts of operational amplifiers. The operational amplifiers are called as op-amps in short, and these are directly coupled high gain amplifiers. Basically, an op-amp will be having multi-stage differential amplifiers followed by level shifters and output stage. The op-amps were originally designed to implement mathematical operations like addition, subtraction, integration, differentiation, etc. But today the op-amps have got versatile applications, like they are used in active filters, oscillators to amplify AC and DC signals and many more. Let us understand the block diagram representation of a typical op-amp. Now here we can see the different stages that are involved in an op-amp circuit. So here we can see the first stage will be an input stage, which is made up of dual input balanced output differential amplifier. So basically this is an differential amplifier in the first stage what we have, and this stage is going to look after the input resistance that op-amp need to be provided, and most of the voltage gain will be provided by the input stage. And this will be followed by an intermediate stage, which is once again a differential amplifier. So this is going to boost the voltage gain of the op-amp after the first stage. And this second stage is going to provide an unbalanced single output, which will be given to the level shifting stage. The output that is provided by the intermediate stage will be well above the ground level, and the logic levels need to be adjusted. So the level shifting stage, where we will be using emitter follower stage, which uses constant current source, will be adjusting the levels with respect to ground. And later on we have the output stage, where we will be having complementary symmetry push-pull amplifier, which is going to provide the current capabilities required by the op-amp. So from this stage we will be drawing the output. So this is the internal block diagram of any op-amp we have. Now this figure shows us the symbol of an op-amp. As we can see here, we have two input terminals, V1 and V2, where V1 is called as non-inverting terminal. This is called as non-inverting terminal, and we have V2, where this will be called as inverting terminal. So these two are the input terminals, V1 and V2, where we apply the input signals to be processed. And here you can see the symbols which says V1 is the non-inverting type and V2 is the inverting type. And this op-amp has got two power supply signals, one is plus VCC, the other one is minus VEE. And here we have the output terminal, V0 represents the output terminal. And here what we have written A, so this A indicates the open loop gain of the op-amp. So A represents open loop gain of the op-amp. Now let us understand the op-amp parameters. So here is the list of various op-amp parameters. Before getting into each of these, let us understand the equivalent diagram of an op-amp. So this diagram shows the equivalent circuit for the op-amp, and this involves the important parameters like Ri, R0, V0 and A, where Ri is the input resistance, R0 is the output resistance. R0 is also called as Thevenin's equivalent resistance R0, and this A into VID is the Thevenin's voltage source. where V0 is the output voltage, and the output voltage V0 is given by this Thevenin's voltage source, that is A into VID, where VID is given by the algebraic sum of the input voltage sources, that is V1 minus V2, where V1 is the voltage applied at the non-inverting terminal and V2 is the voltage applied at the inverting terminal. So basically this op-amp or any op-amp would be sensing the difference between the input voltages applied, and that will be amplified by a gain factor A, and that is what available as output. Now let us get into these parameters. So as listed, the very first parameter is gain. This gain is represented by A. Generally we call this as open loop gain, and this is the ratio of the output voltage to the input differential voltage. So A can be written as V0 divided by VID. So V0 is the output voltage, VID is the input differential voltage. Typically this open loop gain will be 2 into 10 to the power of 5. Alright. So now coming to the second parameter, that is input resistance. So this input resistance is represented as Ri. So here in this diagram we can see, so this is the resistance between two input terminals, or we can also define this input resistance as the resistance that is measured at any one of the input terminals with respect to ground. I mean to say, by making one of the terminals connected to ground, so if you measure the resistance at the other terminal, so we will be getting the input resistance, which is represented as Ri. Typically this will be in mega ohms, so Ri will be in mega ohms. So the reason why it should be in mega ohms is to ensure that the input current that comes in through the terminals to the op-amp will not be allowed inside the circuit. So to make sure this, will make that input resistance is in mega ohms. And the next parameter is the output resistance, which is represented as R0. So here we can see the output resistance R0. So this is the resistance measured at the output terminal V0 with respect to ground, and this will be typically in tens of ohms. So this will just make sure that whatever the current that is required for the output terminal to drive the circuits, so that will be provided. And next one is common mode rejection ratio. In short, will represent this as CMRR, defined as the ratio of differential mode gain to the common mode gain. So this is represented as AD by ACM, where AD represents the differential mode gain and ACM represents the common mode gain. So what is this differential mode gain is, when we have two different inputs connected, the gain that is being offered by the op-amp will be called as differential mode gain, whereas ACM is when we have connected common signal to the input terminals, the gain that is being offered by the op-amp is called as ACM. So the CMRR is defined as the ratio of the differential gain to the common mode gain. And the typical value of the CMRR is 90 dB. The next parameter is slew rate, and slew rate is defined as the maximum rate of change of output voltage per unit time and is expressed in volts per microseconds. So this is written as dV0 by dt max volt per microsecond, and the typical value of the slew rate is 0.5 volt per microsecond. So the typical value is 0.5 volt per microsecond, And the next parameter is bandwidth, and bandwidth is defined as the difference of two frequencies where the gain of the op amp is equal to 1 or remains constant. And the next parameter is the input offset voltage, and this is defined as the small voltage that is required to apply at any one of the input terminals, either V1 or V2, to nullify the output. And this small voltage what we apply is a DC voltage. So this comes into picture when the op amp is working in common mode configuration, and the typical value of the input offset voltage is 6 millivolts DC. And the next parameter is the input offset current, which is defined as the algebraic difference between the currents that are flowing into the inverting terminal and the non-inverting terminal. These currents are represented as IB1 and IB2, and we consider the algebraic difference of these two to represent the parameter input offset current. And the last parameter is the input bias current, which is defined as the average of these two currents, IB1 and IB2. So this is written as IB1 plus IB2 divided by 2. These are the parameters what we have associated with any op amp. Next we'll understand the ideal op amp parameters. So here you can see a list of parameters considered for an ideal op amp. The very first parameter is the voltage gain, and for any ideal op amp, voltage gain is considered to be infinite, which is not desired one for practical applications. So what we do in practical use is we provide an feedback from the output terminal to the input terminal so that it can be controlled. Then the next parameter is the input resistance. Even this is going to be infinite for an ideal op amp. Because the ideal op amp offers infinite input resistance, no current can flow into the op amp circuit. And the next parameter is output resistance. So this is going to be 0. So the output resistance is 0 for an ideal op amp, which indicates that the ideal op amp provides enormous amount of current at the output terminal. And the next parameter is perfect balance, which indicates that the output is going to be 0 when the inputs are 0. And the next parameter is bandwidth. Bandwidth is also infinite for an ideal op amp, which means op amp can amplify any frequency. And next parameter is CMRR. CMRR is also infinite, which indicates that the op amp ideally rejects any common mode signal. And the next parameter is slew rate. Slew rate is also infinite for an ideal op amp, so which indicates that ideally op amp can sense the changes that is happening on the input signals instantaneously and cause the immediate change on the output signal. So these are some of the parameters what we have for an ideal op amp. Now we will understand the open loop configurations of the op amp. There are 3 different modes in which an op amp works, and we name these as differential mode, inverting mode and non-inverting mode. We will discuss one after the other. First, let us take up the differential mode operation of an op amp. So let me draw the circuit diagram for this mode. So this is op amp, what we have, this is inverting terminal, this is non-inverting terminal, and we call this as V2 and this as V1. And in differential mode, we'll be having two signal sources connected, one to the inverting terminal and other one to the non-inverting terminal. So let us consider this as V in 1 and this as R1, and the other signal source will be connected to the inverting terminal V2. So this is the signal source V in 2, and let us call this as R2. And here we have the supply voltages connected. This is plus VCC and this is minus VEE. And here we have the load resistance connected. Let us call this as RL, and here we will be considering V0. So this is the circuit diagram what we have for the differential mode operation. And as we know, op amp basically senses the difference between the input voltages and that will be amplified. So the difference between the input voltages, this one will call as VID. And the output voltage V0 is given by A into VID, which means A into V1 minus V2. And here we know V1 is connected to input signal V in 1 and V2 is connected to V in 2. Though we have the resistances R1 and R2 connected here, these will be negligible compared to the input resistance of the op amp. So the voltage drop across these resistances will also be negligible, will not be having any impact on the output or will be having negligible impact. So substituting these values here, V0 can be written as A into V in 1 minus V in 2. So this is what the output expression is given by. So because here two inputs we are using and the difference between these two is getting amplified, this will be called as differential mode. Now the second mode is inverting mode. In this mode, we will not be using two input signals, rather we will be using only one input signal, and that will be applied to the inverting terminal of the op amp. So this mode is called as inverting mode. Let me draw the circuit diagram for this. So here we have the inverting terminal V2 and this is the non-inverting terminal V1. So because this is inverting mode, we will be connecting the signal to the inverting terminal V2. This is V in, this is input element R, and this will be grounding. The non-inverting terminal V1 will be grounded, and here we have the load resistance connected RL, and this is V0. Now let us write the expression for output voltage. So generally what we have is A into V1 minus V2, but V1 we have 0 because it is ground potential, and V2 is connected to V in. So the output voltage V0 will be equal to A into 0 minus V in, which is nothing but V0 is equal to minus A into V in. So this is the output voltage for an inverting mode amplifier circuit. So here at the output we have a negative sign which indicates that the output will be 180-degree out of phase compared to the input signal. So this is inverting mode operation. Now let us get into the third mode, that is non-inverting mode operation. Non-inverting mode. So here too we will be having only one input signal and that will be connected to the non-inverting terminal, and the inverting terminal will be connected to ground potential. Let me draw the circuit diagram. This is plus VCC, this is minus VEE, and we have inverting and non-inverting inputs. The inverting input terminal is V2, the non-inverting terminal is V1. Input signal will be applied to the non-inverting terminal. So let this be Vin and this be R, and the inverting terminal will be connected to ground potential. So here we have a load resistance RL connected at the output terminal. So here we consider the output voltage V0. Now determining the output voltage equation, V0 is given by A into V1 minus V2, and from the circuit V1 is connected to Vin and V2 is connected to ground potential. So V0 is going to be A into Vin. So this is the output expression for an op-amp connected in non-inverting mode. So here what we can see is output signal is the amplified version of the input signal and is in phase with the input signal. So these three are the different configurations in which an op-amp can work. In the next session, we will understand some of the applications of op-amps. Thank you.